Welcome to Pre-Calculus Live. We are doing this from the NCTM conference in Washington, D.C.
Yeah. Before a packed house.
And we got a packed house tonight. We're really excited to be doing this live with a few folks here in the room. And my name is Curtis Brown, and I've been joined once again by Steve Kokoska and Tom Dick. But this time we get to be sitting in the same room, which is real exciting. Very excited for this evening. Steve and Tom have some great things planned for us. So, Steve, I'm going to give it to you.
Okay.
Take it away.
Thank you, Curtis. Wonderful to be with you here in Washington, D.C., in the basement of the Marriott Marquis. We've got some good problems. I hope you've done your homework.
I did do my homework
Okay.
this time.
Okay.
I'm not promising that I can answer any of the questions, but I did do the homework.
Okay, good. Excellent. Excellent. Well, this first one has to do with transformations of functions, and this is kind of a little bit of a reverse of some of the questions that you might ask your students. You know, often we give them a function, and we give them the graph, and we say, okay, now what if I do this transformation? What does the graph look like? In this example, what we've done is given you a graph of a function f and several transformations, and we want to know how we get there, how we get to one of them. So, for example, in part A, we take a look at y equal f of x minus 4. It might be kind of hard to see up on the screen. If you can see this in color, I think this function f right here is in blue. And what happens if we take a look at f of x minus 4? All right, so the way that I do these problems is I frequently start at the inside and work my way out. So this one's pretty straightforward. It's a shift of the graph, the original graph, a distance of 4 units to the right. So I'm going to take this graph and I'm going to shift it over here 4 units to the right. And that, I think, is graph number 4, labeled as graph number 4. Beautiful. If the eraser works, let's see. Not bad.
Yeah.
Okay. So in part B, pretty straightforward one. So nothing changed to the argument there of f. I'm just taking a look at f of x plus 3. And so that's just a vertical shift of this graph, 3 units up. And I think that's graph number 2. Now they get a little bit more complicated or a little bit more involved as we work our way down. I'll try to keep that graph on the screen as long as I can. So this one, 2 times f of x minus 8. Well, again, I'm going to start at the inside and I'm going to work my way out. And so the first thing I'm going to do is shift that graph, the original graph, a distance of 8 units to the right. And then I'm going to stretch it vertically by a factor of 2. So I look carefully here. I've shifted this 8 units to the right and then stretched it 2 units vertically. So I think that's graph number 5. Part D, 1/2 out in front of the f of x. Well, that's just a shrinking of the graph of y equal f of x by a factor of 2. So let's see. On my main graph up there, I think that would be this one right here, and I think that's graph number 3. Part E, y equal minus f of x plus 4, working on the inside. That's a shift of the graph 4 units to the left, and then there's a minus sign out in front. And what that does is reflect the graph across the x-axis. And so that's got to be this graph right here. So I think that's graph number 1. And then finally, down at the bottom here, we're going to put all of this together if we can in part F. So I'm going to start at the inside and work my way out. I have x minus 8 as part of that argument, so that's a shift of the graph 8 units to the right. I have a 1/2 inside that argument, 1/2 times x minus 8. That's a stretch. That's a stretch the graph horizontally by a factor of 2. I have a minus sign out in front. That's going to reflect it across the x-axis. And then finally a minus 2. That's going to shift it down, shift the whole thing down 2 units. So if I can arrow back up for a minute here, I think that's this final graph right over here. Is that graph number 6, I guess? Right there. So that's kind of a cool question, a little bit sort of a backwards question, and I think there's some very nice things that you can do with technology on both the 84 and a CAS, but I think, Tom, you're going to try this with the 84?
Yeah, I think so, Steve.
Okay.
So,
So I'll turn it over to you.
okay. So the problem that Steve just presented is one where it's really intended to be a problem where you do it graphically, just like Steve was explaining. But if you wanted to use a calculator for some kind of confirmatory checks of your work, it's kind of nice to be able to implement this with the technology. So on the 84, what I'm going to do is actually enter into Y1 a formula for that graph of f that Steve had. And he was kind enough to give us the actual formula he used. Now, it was just it turns out to be a piece of a parabola. So I'm going to show you what the function looks like, but when I say a piece, that means it's only defined over an interval. And so we're going to need to incorporate that. And a way you can have a function that's defined over a restricted domain is by making use of the piecewise function capability on the 84. So let me show you how to find that. So I'm in the y equals menu. And I'm going to go to the math menu. And I'm going to scroll down. And this is pretty far down there, but we'll keep going, clear off past 9. See summation, log base. Yeah, there we go, piecewise. And I'm going to enter that. And let's see. This was.
You're in classic mode, Tom.
That's right. Okay.
So one thing about using the 84 CE, it does matter what mode you're in if you're wanting to use that piecewise function.
I just wanted to make sure people realize.
That's right. This is one of those you did on purpose. You want to make sure you were paid. You were testing me.
Yeah.
I think that's what you were doing. You were testing me. You were making sure that I was paying attention. So yeah, classic mode puts it in there with the parenthesis as a function. So you have to put the rule or the argument in the first section, then a comma, and you put your conditions and continue those in that subsequent order. If you do that now in math print mode, you should get a little bit different.
So I'm pressing the mode key, and you can see that first line was on classic. Now I'm going to change that to math print. Looks good. Now when I go to the y equals menu, you can see the piecewise templates there. And it's in one piece. And I'm going to put in a formula that I think, if I correct, I might enter a little bit different than Steve's expecting, but I'm going to put in a negative 1/3 times 13x plus 4x squared. And then close that off, and the,
oh, you forgot to close the print. Yep.
there we go. Let's try that again. There we go. And
Right arrow. Yep.
now, past the semicolon will be the interval over which that's going to be valid for. And I think it ran from -3, and then we'll need a less than sign, less than or equal sign, and that's going to be under test. And number 6 there, x, and then x will be less than or equal to, so again I'll go to the test menu, get that inequality, and it was a 0.
Yes.
Yes, there we go. And so we'll enter that, and let's go ahead and graph it. I'm going to use a zoom decimal window, I think. See how it look.
Looks
There
pretty
we
good.
have. Okay. Now to get in all the graphs that Steve had in his, we may need a bit different window than that.
For sure.
So I'm going to go to the window, and I think, let's see, maybe just double all these values would be good.
Looks
Okay.
like you have the zoom square window in there, the zoom decimal window,
Zoom
rather.
decimal, yeah.
Yeah.
So let's go like -13.2.
If you just arrow down and right arrow to the end of that and hit ×2, it'll
That's a
evaluate
nice
that
thing.
and put it
It'll
in
go
there.
ahead and just do the calculation. That's an easy way to double all the existing settings.
Put in your ×2s.
And as soon as I hit enter, it goes ahead and calculates that. By the way, that's particularly good if you want to enter, for some reason, maybe with the trig function, you're entering actually pi. You just do the pi symbol, and then when you enter it, it'll put in the 3.14, 159, and so forth. Okay, so let's take a look at that graph again. And now that gives a little more real estate to work with. But now if we wanted to check our whether we matched up with the ones that Steve had in his picture, we could just go to the y equals menu, and in y2, for example, let's look at part A. He had the f of the quantity x minus 4. We're just going to use y1 of the quantity x minus 4. Graph it, and there we go. We can check and see that shift there. Okay, let's do maybe just one more, and then I'll turn it back to Steve. Go back to y equals. This time we'll use y3. Maybe do one of the ones that was a little bit more involved. Let's see, maybe. Part F was quite a bit. Yeah. Okay. So that's a negative y1. And that was of one half times x minus 8.
Maybe a parentheses in there?
Oh, good cat. I actually just misread it. So let me insert a parentheses in front of that x. There we go. 1/2 times the quantity x minus 8. And that's all inside the parentheses of the function argument.
Right.
So enter that, graph that, and there we go. And it's kind of nice on the 84 CE, the color edition, it kind of automatically, each successive function is in a different color, makes it easy to distinguish. So again, that's a nice way to just do a graphical check. You do need to have some kind of a formula for your function, but even if it's just defined over an interval, that piecewise is a nice way to take care of that.
Before you leave that, Curtis,
Yeah.
One thing I think might be nice on yours, can you put the grid on?
Yeah. So one thing that is kind of handy is to use the grid during these sessions. So if you'll press the second key, Tom,
Yep.
and then the zoom for format, second and format. Underneath of format menu, you've got an option to use the grid line. So if you arrow down a couple there, you'll see that you've got grid dot or grid line, either one of those.
So grid dot will look like dot paper.
It'll look like dot
it'll be
paper.
at the integer values.
At the integer intersections, yep. And then
So
grid
grid
line
line.
actually there. And you could change that grid color depending upon, if you're doing a projector in your screen in your classroom, you can darken it or lighten it depending upon that. And the same thing on your graphing calculator as well. So it makes it nice.
Fantastic.
Good thought.
And I'm noticing here we can even change the color of the axes or whatever.
Change the
Yeah, lots of
axes to
things.
make them,
Yeah.
stand out a little bit different for sure.
All right, so let's go ahead and
Yeah,
look at the
let's see.
graph with the grid line.
Yeah,
Ah, nice. Okay.
that does help.
And that's very handy for problems like this where you're doing these shifts and flips and things to count the units. that you're-
I'm going to point one other thing out. So naturally or natively, the standard window on the TI-84 is not as square as this.
Yes.
And so it's really nice that you've got a nice square window. So all of those grid points or grids are now square. So zoom decimal really gave you that ratio that was appropriate.
Yeah, and that's a good thing to bring up. The standard window on the 84 is actually runs from -10 to 10 in the x direction and -10 to 10 in the y direction. But because the screen itself is not a square, that means you're going to have some kind of unequal scaling in one direction. And that distorts the graph, especially if you're trying to read things like slope and things like that. So I really do prefer that zoom decimal window. It gives you that nice equal amounts for one unit in both directions. All right, Steve, I'm going to turn it back over to you.
Thank you. All right, well, one of the other topics that we're talking about tonight is combinations of functions. And so we've got a couple of problems here. There's actually 4 of them in here, but we'll only get to 2 of them tonight. and then we'll do a little bit more technology. So I've got some functions f and g, and I want to take a look at the sum function, the difference, the product, and the quotient. And some of these are pretty straightforward, but I'd also like to think a little bit about the domains too along the way. And for me, I really need to graph some of these to see what's going on, see if I can justify my answer, if it's possible to do that graphically. So the first one, we have two exponential functions, 2 to the x and 3 to the x. The sum function f plus g is just f of x plus g of x, and I don't think there's any simplification that I can do in there. I'm going to have to leave it like that. And what's the domain? Well, the domain for each of these functions is all real numbers. The intersection, of course, all real numbers. So the domain here is all reals. There are no restrictions. If I take a look at these graphs, f is the one down below here. Here's g, and f plus g. Well, this sort of makes sense, I guess. If I were to draw a vertical line here at a value of x, can I see that that value up on the f plus g curve is the sum of those two? I think so. One thing that you might investigate with your students tomorrow morning, or maybe Monday morning when you get back to class, one thing you might think about is, well, what's going on over here to the left of x equals 0? In other words, which function f, g is above the other? Which one is the greater function, has the greater value at a particular value of x? So you might think about that and just make sure that, yeah, I see the sum function over there. Perhaps you'd use technology to zoom in a little bit to make sure. So as I arrow down at the bottom, down towards the bottom here, we'll take a look at the difference function. And again, nothing too deep here. I don't think I can do any simplification. And once again, the domain for this function is all real numbers. Here's f, here's g. And this time the difference looks like this. There's f minus g. Does that make sense? Well, let's see. At least to the left of x equals 0, the function g is greater than the function of values on g are greater than the values of f at a specific value of x. So yeah, when I do that, take that difference, I'll get a negative value. So that makes sense. It's kind of, once again, difficult to see what's going on over here on my graph. So we'll leave that as sort of an open question, one that you might investigate with your students. What's happening to the left of x equals 0? What's happening to this difference function? Does it look like it's zeroing in on any one particular number? Does it look like it's getting closer and closer to 0? Maybe as x decreases without bound, there is some sort of, well, quote-unquote limit. So something to think about. Let's take a look at this one, the product function, f of x times g of x. Fg of x is f of x times g of x. Well, a little bit of simplification here. I think that's 6 to the x, but the domain, once again, is just all real numbers. And the graph isn't too bad here. I included that. You can see f, you can see g, and there's f times g. That, of course, to the right of x equals 0 increases much quicker, gets larger quicker. And again, I guess I pointed this out a couple of times, but you might think about what's going on over here also. Which of these functions, at any particular value of x, what's the order of them? And finally, this is kind of a cool one down towards the bottom. The quotient function, f divided by g, is just f of x divided by g of x. And here I could rewrite this a little bit as 2/3 to the x. The domain here is all real numbers. And let's see if I've got this right here. There's f and there's g, 2/3 to the x. Let's see. What happens as x increases without bound? Well, that's 2/3 times 2/3 a lot of times. And let's see, since that fraction is less than 1, that must be getting smaller and smaller, closer to 0 as x increases without bound. It's a little unclear from my graph what this quotient f over g is doing to the left of x equals 0. So I don't know whether Tom will look at this with technology farther to the left there or not, but that's an interesting question too. And maybe, can you tell by just looking at this simplification, what happens to that expression as x decreases without bound, as x gets larger and larger negative? Cool. I'm going to do one more before we try a little bit of technology, and there's some interesting things that happen with this function, or these two functions, excuse me. So we've got f equal to the log base 10 of x. We've got g equal to the natural log of x. And let's try the same four things. Think about the domain. Think about these graphs. F plus g, the sum function, is f of x plus g of x. That's the log base 10 of x plus the natural log of x. And I don't see any simplification there. The domain here has got to be x greater than 0 because, well, that's the domain of each of these individual functions. We've got to take a look at the intersection here, and it's just x greater than 0. And I've graphed f and I've graphed g here, and there's f plus g, and I think I see that well to the right of 1. It makes sense to me. I guess I've got to think a little bit over here to the left of 1, or between 0 and 1. Do those graphs make sense? I think they do. I think everything's okay there. Let's take a look at the difference, f minus g. Well, that's just f of x minus g of x. And here's some neat things begin to happen. Well, no simplification there. The domain is still x greater than 0, but take a look at this resulting graph. F minus g is really this one. All right, Curtis, I haven't asked you any questions
I
tonight.
know. You've been leaving me alone. This is great.
So
I've been not picked on tonight. What's happening?
So does that make sense? Let's see. Does that make sense? Well, to the right of 1, let's see, g is greater. The graph of g is above the graph of f. So when I do the difference, I certainly get
I agree with that.
Okay.
Totally
so
agree with that.
what about between 0 and 1? Can we see that? Let's see. Let's see. Which one's f and which one is g?
So f is the blue graph, right?
Right.
So it's larger.
Okay.
Between 0 and 1.
Okay.
Right? And we're doing f
minus g.
F minus g. We're doing f minus g.
So f.
If f is greater magnitude, lesser magnitude, right? So it is above.
Yes.
But remember, we're on the negative side, right? So we're taking a small negative, closer to 0 negative number.
Yes.
And subtracting off a larger or a farther from 0 negative number.
Right.
That added together does seem like it would increase, right?
Produce a positive value.
But I had to think about that, and
Very
a
good.
way to say that too.
Very good. Okay.
Yeah, that's a good question.
Okay.
That's interesting.
All right. All right. I got another one for you.
Oh man.
How about f times g of x? Well, that's the log of x times the ln of x, and I don't see any simplification there.
But that makes sense.
What does?
Well, the graph that you've got there.
Oh, okay. All right. The domain here is x greater than 0. All right. Does this one make sense? Well, let's see.
It does.
This is f times g right in here. And then as we get to the left of 1, between 0 and 1, it increases very rapidly, it looks like, goes up to plus infinity. Does that make sense? Well, because both of these functions are negative, and I'm multiplying those two together, resulting in a positive value. So, yeah, I think that's okay. That one makes sense. And here's the really interesting one, if I can arrow up here. How about this quotient? F over g of x. That's f of x divided by g of x. Well, that's the log of x base 10, log base 10 of x divided by the natural log of x. And what's the domain here? I have to be very careful about this. It is certainly greater than 0, but why can't x be equal to 1? Why do we have to exclude that from the domain?
What happens in the room? Why do we have to exclude
X equal 1.
x equals 1?
Because the denominator
Because the
would be
denominator
0.
is 0.
Very good. Excellent. Excellent.
But why is it horizontal?
But why is it horizontal?
Why is it horizontal? The question in the room was,
That
why
is
is it
an
horizontal?
amazing, this is an amazing question. First of all,
Any good reason?
I think there might be one. When I graph this, I got a straight line, a horizontal line. There is indeed a hole right here, if you can see it, above x equal 1.
Yeah.
And in the strictest sense, perhaps this wouldn't be called a hole, but when I graph it, I'm going to put an open hole there because there is no part of this graph to the left of x equals 0.
Or at 0 itself.
Or at 0
Or at
itself.
0, yeah.
So why is this a constant?
What happened?
What happened, Curtis?
What
I think
happened?
this is correct.
Yeah,
What
what
happened?
happened?
Change of base, like log base 10 of x over log base e of x.
Beautiful.
So I'll
Excellent.
repeat that for everybody on the chat on the live stream.
We can't hear them at all on the live stream, so you'll have to repeat.
Right.
Okay.
Log base 10 of e, right?
So we have so we need the change of base,
We
right?
needed
This
the
is an example of change of base. So we need log base 10 of e, right?
10 to the 1 half is the square root of 10. It's a little bit more than 3. E is 2.718. We should be a little bit smaller than 1 half.
Very
Okay,
good.
so a little bit smaller than 1/2 because
Because the square root of 10
square root of 10 is roughly what? 3. It's larger than e. So
Very good.
yeah. Good.
Wow. Okay.
Listen to that. I mean right?
Okay. So a couple of little things here before I turn it over to Tom, and maybe he'll take a look at some of this. I'm not sure. When I graphed this originally, I was using Mathematica, and when I graphed this, it actually gave me the correct function f and the correct function g. But in fact, it graphed this horizontal line all the way to the left. It kept going forever and ever to the left. And that's certainly not right because the domain here is x greater than 0, x not equal to 1. And so an open sort of question is, why did that happen with Mathematica? So that's just a good example as to why you need to think carefully about what is the domain of one of these combinations of functions. Now here's one other thing that you can think of. We know that many of our pre-calculus teachers also teach calculus. And so you might think about, I'm going to scribble a little bit off to the side here, you might think about the limit as x goes to 0 from the right of the log base 10 of x divided by the natural log of x. As x goes to 0 from the right, both of these expressions are decreasing without bound. So both are going to minus infinity. So this is indeed, what is this called, Curtis? Right, an indeterminate form. Very good. Excellent.
You caught me while I was
Excellent.
looking at the chat. I
Excellent.
wasn't listening to
Excellent.
what you were saying, Steve.
So, but that, it's just a rowdy crowd.
I mean,
Man.
we got some rowdies
Holy
in here
Toledo.
tonight.
So, if you were in teaching AP Calculus, you would recognize that this is an indeterminate form, and you might want to solve this limit by using L'Hopital's rule. And in fact, this graph is kind of a visualization of that result. And the result you'd get from taking the derivative of the top, derivative of the bottom, would result in a constant.
That
is
was,
really cool.
man, that was a shock for me whenever I saw that when we saw that this morning, because
about it.
I didn't do all of my homework. I only did most of my homework, and I hadn't seen that yet. That was really cool.
It was very nice. All right, Tom, I'm going to turn it over for a little technology, okay?
Okay.
Beautiful.
All right. Okay, so I thought what I would do with this one is stay with these logarithmic functions that Steve was looking at, and take a look at both the 84 and the TI-Nspire, how you can deal with these different logarithms. So on the 84, the logarithms that are just available straight off the keyboard are the common log, which is log base 10, and the natural log, which is log base e. So let me bring up the common log, and let me put in a nice power of 10, since this is base 10. So I'm going to put in 100, and we want to think, okay, log base 10, this should be, what would be the power you would raise 10 to get 100? So if we think through that, we should get, well, 2, because 10 squared is 100. Similarly, natural log, and this is what may seem pretty strange to kids is it uses a base that's a very strange number. It's actually an irrational number. This e that's 2.718 approximately. So if I want to get a nice value for the output of the natural log, I'm going to need as an input a power of e. So I'm going to bring up e to, and I'll put in, let's see, maybe 3, e to the third. And this is going to seem maybe silly, but I'm asking what number would you raise e to get e to the third? Well, that's pretty self-evident. It's going to be 3. And sure enough, oops, let's just go ahead and enter that. There we go. Now you may be saying, well, are those the only logs you can do? And the answer is no. You could use a log of other bases. And I just want to show you quickly kind of where to find that. That's going to be under your math menu. So if you pull up the math menu, that's where we got the piecewise a little while ago. And I'm looking, I don't see any logs here, so let me just keep scrolling down until I find, let's see, summation. Ah, there we go, log base. That's it. So that's the function we're going to want.
So that's a log of a specified base.
A specified base.
Yeah, yeah.
And you can notice that it brings up a log where the base is left for you to fill in. Now, if there's nothing there, we notice that it's commonly understood, pun intended, that's its common log base 10. But now we could put in something like log base 7. And then we could say, well, what's log base 7 of something like 49?
So hold on, Tom. I want to show, so you showed how to find that underneath the math menu.
Right.
But there's also a really nice way to get this where you can get it in a recognizable form as well. So log base might not be a menu item that folks would recognize right away. Mm-hmm. If you press the alpha key,
okay,
and then choose the F2 menu, alpha F2.
Okay.
You can actually pull that log of a specified base right off of here, but you notice on the right-hand side, you've also got the template already pulled up for you in blue. You've kind of got that template already showing. It's a really nice way to see those templates in the form that they're going to show up on the actual math print.
So these are the math print.
So those are the math print versions. It's really kind of a nice little piece of that. Rather than grabbing it off the math menu, which is a great place to get it. If you press alpha and that F2 function, you'll get those menus with the math print.
That's a nice, nice shortcut too. Okay, great. Okay, I want to take a look before we leave the 84. Let's go ahead and do that last problem Steve was looking at, which I found really kind of fascinating. That was to take the common log of, let's see, excuse me, there we go, common log of x divided by the natural log of x and we just do a zoom decimal window. It's kind of my tried and true window. And notice on the 84, if you use something like a zoom decimal window where if your discontinuities occur right at one of the pixel values, it'll actually show up as, in this case, it's a removable discontinuity. We see that hole. And we also see it doesn't quite reach over to x equals 0. Mm-hmm. So it's actually showing those graphical characteristics. So, and in fact, let's see, I'm going to say what is the value of that constant if I actually trace. Notice that when I start out the trace at x equals 0, there is no y value. That makes sense. Y is not defined there. Mm-hmm. But as I trace to the right, I'm always getting the same value. It's this 0.43429. I think that's somebody in the audience offered it had to be something a little bit less than half, so it's really looking good. In fact, I think somebody identified what number that would actually be. I think it was going to be the common log of e? Okay,
Log
well-
base 10 of E. Well done. Well done.
well, let's
we need to
check
give
that
that
out.
audience
Let's check
member a
that out.
prize.
Let's check that out. All
Yeah.
right, so let's go.
Let's
make
just
sure.
see. I
So I'm
mean,
going to
Yeah.
use the common log
we don't want to just believe everybody.
of E. I'll put in E to the first. There we go. All right, looks very good. Very good. All right.
Well, wait a minute. We've got a graph head or something, don't we? To double check him?
Well, we already had a graph up there.
But how?
You're going to trace that?
We're going to trace that? Okay. All right,
Okay,
all
now
right.
we verified
Now
it.
I'm okay.
Now you verified
Now
it.
I'm all right.
If you really wanted to verify that, you could go back to you could go to the home screen and type in y equals and then pull that menu down and check to use the the binary
Well,
operator and
I'm
test
okay with
test
this,
that.
yes.
But I think we don't have to do that.
Okay.
Very good.
Some people were giving me a little bit of a hard time in the audience here, by the way, about me always looking down on the computer and typing. It's because there's stuff going on in the chat, so I don't want you guys to think I'm just ignoring you.
Related to this.
Yeah, related to this. I'm not just chatting about,
Okay.
other,
Okay.
but no, related to this.
Okay.
All right. Okay, can you stand a little bit more, Steve?
Oh, absolutely.
All right, we're going to look at the function transform app. All right.
Yeah.
Okay. So I'm going to pull up an app that's really nice for doing transforms of functions. So I pull up the application menu, and as I scroll down, the one I'm looking for is the transform app. So let's bring in that, and we get this big screen here. And let's take a little bit of time. I want to talk a little bit about this specifically for transformation graphing. It says for animated graphing, the X resolution has been set to 3. And not everybody understands what that is referring to. XRes refers to what's the kind of the skip between pixels that values are actually calculated. And with an XRes of 3, you're going to get graphs will graph 3 times as fast as normal, but it could also be a little choppier looking, the graphs could be. So I'm going to actually set the XRes back to 1, that's the normal, for what we're going to look at next, okay? Now I'm going to go ahead and press another key. We've got the math app on now, and let me go to the Windows settings. And you can see down here at the bottom, near the bottom, XRes is set to 3. I'm going to go ahead and set that to 1. That'll be just our normal graphing.
Okay.
And then I'm going to go to y equals, clear out that first one. And if you look real closely at this, y1 and y2 have a little bit different symbol to the left of them. Okay, these are the functions that are active for the transformation graphing. And so what I'd like to do is actually put in a log base A. In other words, I don't want to specify what the base is. So let me get that log base. I'm going to do it the not Curtis's quick way. I'll just go ahead and get it off the math menu again. So I've got log base, and instead of putting an actual number in there, I'm going to put A. And then our argument is X. And then when I pull up a graph of this, here you can see what it looks like if I guess it's called classic mode, log base X, and then you put the base after it. Now A did have a value, it turned out. A happened to be 3. That's because all the variables A through Z on the 84 have some value in them at all time. I think the default is 0.
Is 0.
They stick around until you set them to something else. But what's nice now here is I can change the base by just using the left and right arrow keys. If I hit the right arrow key, the base increases by 1. So now that's a log base 4 of X. And here's the log base 5 of X. Now I'm going to try to do that a little bit more quickly so you can see it graphing. And now I'm going to back it up. And if you look at it, notice that all these graphs go through the point 1, 0, Oh, when I hit a equal 1, let's see, log base 1, does that, I guess that doesn't make any sense. Does it make sense that it doesn't make sense? That's what.
So wait, the
Oh,
base is
one to any
1.
power,
Oh,
yeah, it's not
one.
going to be
Yeah.
an interesting function at all. But this is something, it's related to this change of base thing, but I think it's something that maybe not everyone appreciates is every single logarithmic function is a vertical dilation of another logarithmic function.
Say that one more time, Tom.
So every logarithmic function, so logarithm base 3
Yeah.
is going to be a constant multiple of the natural logarithm.
Right, change of base. This is
Correct.
we're going
But
back
that's
to
what
that
that
change of base thing.
But it is a
I had to make
constant,
sure that
yeah, it's
I was thinking about that the right way. So it is,
Yeah.
but it's a yeah. Okay,
constant,
okay.
yeah.
So it's constant across the whole. Yeah.
Right.
Right. So it's vertical dilation.
And that means
or scale
basically
change.
that every logarithm is a multiple of every other logarithm. Just a simple constant multiple. So
That's
it's
right.
really kind of a cool thing. And so if we were to go to the y equals, and I'm going to now edit this, make it log base a of x divided by the log base b of x.
We're waiting with bated
Okay.
breath in the room
So
here.
both of those variables show up below.
Both those variables show up. I don't see any graph, and the reason is b happened to be equal to 1,
Gotcha.
which it doesn't make any sense. So let me make b equal to 2. And we get something that looks like that graph we had before. It looks like a horizontal line, except it's only for x greater than 0. There's a hole at x equal 1.
Right.
But other than that, it's a perfectly flat line. And it doesn't matter what value I change b. If I change b to 3, b4, I'm getting different constants with a hole in them. And those are all representing that fact that our logarithms are constant multiples of each other.
Is that a realization for everyone else in the room? Like in the room, like
I thought
for
it was
me, I don't know if this
a
is
neat
like
idea.
I mean, this is just kind of a really cool thing that I wouldn't have thought. It makes perfect sense now. Like
Yeah.
but I never would have thought of this without having seen that graphically in Steve's question of making us play with this a little bit at the very beginning.
Right.
I wouldn't have thought of that. First time.
First time. Okay.
So-
now,
I'm
go
sorry.
ahead,
So
Steve.
Tom, before you leave this, or maybe you're going to do this, but how many variables are you allowed in this transform?
The transform app allows you to have up to 4 different variables
Okay.
involved. 4 different, I should say parameters, because the A, B, and they have to be, you can use any letters you want as long as they're A, B, C, and D.
I see. Okay.
So
Okay.
it's a limited choice. But there's quite a bit of stuff you can do with those.
Sure. Sure.
Now I'm going to change over to the Nspire just briefly here,
Okay.
just to show kind of what this log looks like on the Nspire. So I've got a similar keyboard, and I see the log key here. It looks like common log, but what's interesting here is if I hit the common log key, so that'll be a control. Notice what happens here is I actually get a little subscript for the base, but it's actually gray. I don't know if you can see that. I hope you can see that on the screen.
Mm-hmm.
A grayed in box means it's an optional thing that you can fill in. Now, if you don't fill that in, it's going to assume it's a common log. That's log base 10.
Log base 10,
So I'm going to
okay.
leave that like it is. Move up and say, let's try that. Let me put in 1,000 to just check it out. Now that, I know what the log base 10 of 1,000 is. Let's see, 10 to the third is 1,000, so I should get a 3 if this really is log base 10. And in fact, when I enter it, notice what happened to the base. It actually filled in for me. It says, okay, I'm assuming it's a 10. But if you bring up that log and fill it in, you can fill in that optional box with whatever number you want. So if I put in like a 5, and then put in something like 25, it does the log base that. And then natural log is also another function that I can do. Okay, so a slightly different behavior there. But Steve, I think it's probably time
Okay.
I turn it back over to you.
All righty. Okay, well, let's do a little bit with composition of functions. Another way that we can combine a couple of functions to create new ones. And I'm going to try a couple of these, and if we have some time, we'll do some technology. If not, we'll get to some of the other problems. Here we have two exponential functions, 2 to the x, an exponential function 2 to the x and a linear 3x. And let's take a look at 4 different ways to combine these two functions. So f circled g, f composed with g, is f of g of x. So that's f of 3x, and that would be 2 to the 3x. And I think I scribbled off to the side here, if I want to simplify that, I think I can rewrite this expression like this, 2 cubed, all of that raised to the x power. That's a property of exponents. And then that would just be 2 cubed, which is 8 to the x. I can think a little bit, and I should think a little bit about the domain here. I believe that's all real numbers. There's no restriction here on g. And yeah, we can take 2 raised to any power, positive or negative, even 0. And so the domain is all reals. I graphed these 3 functions, f, g, and f composed with g, although I don't know if there's an easy way to see what f circled g would look like from the graphs. Although, an exercise with students is to try to find an example of like f circled g of 1 or f circled g of 2, a possible value. Can you use the graphs to figure this out, maybe even without f circled g on here? That's a possibility. All right, well, how about, let's see, g circle f? Well, that would be g of 2 to the x. And remember, g was just this linear function. I'm going to scribble a little bit off to the side. Remember, g of x was just 3 times x. So we have to evaluate g at this argument, so that's just 3 times 2 to the x. And I don't see any good simplification there. Domain is all reals. Yeah, that's pretty straightforward. We've just got that exponential to worry about. That accepts all values. And here are the graphs of those 3 functions. Beautiful. All right, how about f circle f? Can you really do this? Sure. You can compose a function with itself, and in fact, I don't know if we'll get to this evening, but you could do f circle f and continue and do that. Continue to compose a function on itself. So this would be f of 2 to the x, and let's see, that's 2 to the 2 to the x, and I don't think there's any simplification there. So this function, f circle f, I've graphed it over here. This really grows very quickly as x increases without bound. And it does look like that this might be getting closer and closer to the x-axis, but I'm not so sure. I wonder what's happening to those values of f circle f as x decreases, without bound. Any idea on that one, Curtis?
What are we talking about? You got me distracted on the chat. So there's 2 things that have been going on in the chat. You don't know
What?
this.
Okay.
There's 2 things that have been going on in the chat. First of all, we had this poll.
Yes.
We were asking the question before the session. In the room, we were asking the question
Yes.
if it was pre-cal or if it was pre-calc.
Okay.
We posted a poll in the session.
Yes.
The poll is closed.
Yes.
67% of the people agreed with all you bums that said pre-calculus. See, pre-calc with a C,
Okay.
which means what? 33% of us got it right. But that's all right. So that was 2. And then there was a comment that there's Tanya in particular has been thinking about that change of base with the derivatives thing and seeing
good,
that was
good.
a great piece. So I apologize. I was responding to some of those things, thinking about that. What was your question to me?
Here's the question. So we've got f circle f, and it turns out to be 2.
2 to the 2 to the x. Yeah.
Okay. So what happens over here as x decreases without bound?
So this was kind of an interesting one,
Yes.
right? So 2 to the x should, just by itself, 2 to the x should go or approach 0, right?
Correct.
As x goes to negative infinity, decreases without bound.
Correct.
Should go to 0.
Correct.
Which means that we're
Yes,
talking
yes.
about 2 to the approaching 0.
Right.
So it should go to 1.
Beautiful. Good argument.
Does that make sense?
Yes.
Okay.
Okay.
Made sense to me, but I had
Very
to think
good.
about it.
That's a real good one, a good problem, I think, to consider with your students.
For sure.
All right, G circle G is not that difficult. This is just G of 3x, which is another 3 times 3x, 9x.
Perfect.
So that's a pretty straightforward one. That's a linear function also. Okay, I've got one more here that I want to take a look at. Let's introduce a log function here. Let's take a look at f 2 to the x, and g is the log base 10 of x. So f circle g of x, that's f of the log of x, that's 2 to the log base 10 of x. Well, I'm not going to try to simplify that, but I do want to think a little bit about the domain here. Well, let's see. The domain for that function is all reals, but the domain for the log is x greater than
Greater
0.
than 0.
Right. And here's some graphs. Some interesting things happen here. Let's see. There's a f. That's the exponential function. Here's the graph of g, which is the log base 10. And if you can see my f circle g, I've actually drawn this with an open circle right here at the origin. Does that make sense? All right, Curtis, this is your cue.
Does that make sense?
Can you
My cue.
can you reason
Can
that
we
one?
can we reason what's going on here?
Yeah, and
So
I'll add
as
it
we
in.
well, let's approach it from 0 from the positive side.
As x approaches
That's what
0
I was.
from
Yeah.
the right.
So
what's
as we
happening?
approach this from the okay, so we're thinking about 2 to the log x. So as log x as we approach from the positive side. So let's think about what happens there in that exponent. Log x as we approach from the positive side takes off to negative infinity. Yeah.
Good.
Okay. So 2 to the negative infinity, right? So
Okay.
we're gonna go towards
Okay.
negative infinity. 2. We're gonna approach that. It's gonna have to take off towards 0. It's
Okay.
gonna approach 0.
Okay, so
But I can't get to 0,
No.
right? Because I've got that vertical asymptote in G. So it's not, that's domain restrictions. That's why the open. That's why the open circle. So
Okay.
yeah, it does make
very
sense.
good. This is an interesting one to me because g decreases without bound here, and yet when we take a look at f circle g,
You end up with a hole.
you end up with a hole in the
Or
graph
a-
there.
Yeah, yeah.
Yeah.
That
That's kind of
struck
a nice
me
one.
a little bit interesting.
All right, let's take a look at
So hey, you got about 5 minutes. I'm
Okay.
just telling you.
let's take a look at g circle.
I mean, we could do overtime and we could go a long time, but they're going to kick us out of the room.
Okay,
And we got a
gotcha.
lot of people to get out.
I got you. Okay.
So-
I got you. All right, g circle f. That's g of 2 to the x. That's the log of 2 to the x, and a little bit of properties of logarithms. And son of a gun, this is just a straight line through the origin. Log base 10 of 2 times x. That's a nice problem. Let's take a look at f circle f of x. Well, I didn't do anything here because we already did that one. We did that one up in part I, or I believe the first part of this problem. So we're not going to do that one again. But how about the log of x? That's g circle g of x. Well, the domain there is x greater than 0. Pardon me, is log of x greater than 0. And where does that happen? Only if x is greater than 1. So this is actually the graph of g circle g right here. And I'm going to scribble in a little bit. It certainly looks like there is a vertical asymptote there at x equal 1, but you might think a little bit about that one. I won't put you on the spot for that
Well, I
one, Curtis.
appreciate that.
Okay, I'll leave that. All right, so there are a lot more problems here. We've got a little bit with inverses. And before we leave tonight, I would like to take a quick look at some of these overtime problems. These are problems that have appeared in the AP Pre-Calculus Facebook group. And there's been some discussion about some of these, and I thought these were kind of nice or demonstrated a nice concept. So I wanted to show you just a couple of these, leave you with a couple of questions, and this was one of them. Here's a piecewise defined function. One of the pieces has an absolute value in it. I remember my college calculus professor telling me that whenever you have a problem that involves absolute value, generally what you need to do is to work to get rid of those absolute value symbols in some way. And what does that mean? Use the definition of absolute value to try to get rid of them. So I, in fact, did that and followed his advice, and I tried to rewrite this piecewise defined function without the absolute value. I did that because I thought about, well, if x is less than 1, then that argument inside the absolute value would be negative. So when I take the absolute value of it, I have to put a negative sign out in front, and I did a little bit of simplifying, and I got this. This question, I believe the original question asked, where is this function increasing or decreasing? So I did a little bit of simplification, and I believe the only way that we can answer this in a pre-calc class, excuse me,
Oh my
is
goodness.
to graph this one. So I did
No.
that. I did that. It looks like a cubic function coming down here. It is a continuous function. And I pick up to the right of 1 with a linear function like that. Well, look, I see this linear function over here. That has a slope of -2, so that's certainly decreasing. Looking at the graph and knowing about the nature of a cubic function, I've got that negative sign out there, this is certainly decreasing. So in fact, the answer to this problem, the way that I see it, is that this function is decreasing over all reals from -infinity to +infinity. Now, a question that came up in relationship to this problem was something like this. I'm going to change the left piece just a little bit. And I won't give you the description of this analytically, but let's suppose that the left piece is just shifted up vertically, let's say 3 or 4 units. There's an open hole there above x equal 1. There's a solid dot here, and we still have that graph -2x to the left, pardon me, to the right of x equal 1. The question is this function still decreasing over all reals, even though it is discontinuous, not continuous at x equal 1? I believe the answer to that is yes, and the reason is, the justification is, that, well, that's just the definition of what it means for a function to be decreasing. As I move left to right, are the values getting smaller? And indeed they are. So I believe that's true. This function is indeed decreasing over all the reals. Here's another very interesting one that came up. This is an example of the question that came up. I'm going to take a look at the function x -2 divided by x -2 squared. So this had to do with, well, can you have a whole and a vertical asymptote in a rational function? I believe somebody used the idea of, well, vertical asymptotes trump wholes, and I'm not going to get into that kind of lingo, but here's what I see in a problem like this. One of the x -2's will cancel. And that suggests that there is a hole here above, somewhere above x equal 2. But when I cancel those, I'm still left with an x -2 in the denominator. And that tells me that there is a vertical asymptote at x equal 2. So there's no hole in the graph of this function, and in fact it looks like this. As x approaches 2 from the left, the graph is decreasing with outbound. As it's approaching 2 from the right, it's increasing with outbound. So no hole there. However, I did wanted to point out, and Tom could probably come up with a function that's defined that is not piecewise, but here's a crazy function that is a piecewise defined and has a vertical asymptote, has a hole in the graph, an open circle in the graph at x equal 2, and a solid dot. And one question that you might think about, especially if you're teaching calculus, AP calculus, is x equal 2 really a vertical asymptote? Can we call it that if I have a function defined like this? And finally, one more, and we'll call it a night, Curtis.
Sounds good.
This is a typical sort of a question that you would see on an AP exam. Here's a function f, and you might say, oh, I know all about that function, but it's really not f we want to know about, it's h. And in this case, h is 2 times f of 3x. So this kind of brings into some of the things we've been talking about this evening. So this is a transformation of that original function f. But what I really want to know about is the intervals on which h is greater than or equal to 0. My point in solving this problem is, well, I figured out exactly what h looked like, and I factored it completely, and I used that factored form to construct a sign chart. We know that sign charts are not acceptable justification on the AP Calculus exam. They're probably not going to be acceptable justification on the pre-calculus exam, but there's no harm in using one. It's very useful to have one. So I used a sign chart just to figure out the sign of h of x in these intervals determined by the zeros of the function. And looking at that sign chart, I determined that h of x is greater than or equal to 0 on the interval minus infinity to 1/3. I graphed these two functions just so you could see that, just for my own benefit, really. And yeah, it does indeed look like I've got that correct, that h of x is greater than or equal to 0 on that interval. Fantastic. Thank you, Curtis.
This
Tom?
was fantastic. Thank you guys both very much for doing this. Thank you guys for
Thank you.
attending. I have two last things. Two last things. Good grief. I've got two last things on this session. So the one thing I want to make sure, so Steve, we
Yes,
are going to
sir.
post, we did post already the questions that we had ready to go.
Yep.
But the overtime questions that you got from the pre-calculus listserv or
Yes.
the Facebook group, those questions will be posted as a part of the solutions.
Yes,
Is that
they will.
correct?
Yep.
So we'll have those posted as a part of the solutions. We're going to make sure that we have those in the morning. I'll get those up there and posted, ready to go on the description for this live stream event. And again, if you guys have attended or watched the whole session, please send me an email at curtis@ti.com. Really excited to get those emails, send you guys out that certificate. And so go ahead and join us here on November 30th, I think, is the next pre-cal live session. And for our AP Calculus teachers, we'll see you Monday night.
Fantastic. Thank you.